On October 29th, a date you'll want to remember, the interstellar object known as 32E Atlas is going to vanish. It will slip behind the sun, completely hidden from our view. Now, at the exact same time, a fascinating, and frankly, a bit unsettling theory from researcher Avi Loeb suggests this isn't just a simple flyby. He claims this massive, fast-moving visitor could use the cover of the sun to perform a hidden maneuver, a maneuver that could trap it in our solar system forever. The official story is straightforward. 32E Atlas is just a comet, passing through our cosmic neighborhood before heading back out into the void. But the early data makes that story hard to swallow. We're talking about a nucleus possibly 20 kilometers wide, weighing more than 33 billion tons. It's an absolute giant. Yet, despite showing eruptive outgassing, like a comet should, it displayed almost zero non-gravitational acceleration. It's like a car sputtering and smoking but continuing to coast perfectly straight, as if the engine isn't really connected. This just doesn't add up for a typical comet. So what's really going on? Is it a rogue comet behaving strangely, or is there more to the story? If Avi Loeb is right, we might be about to witness the first interstellar visitor to become a permanent resident of our solar system. And the most frustrating part? We'll have no way to watch what happens during that critical moment. What are we going to miss during that solar blackout? And who will be proven right when Atlas finally re-emerges from the sun's glare? October 29th draws a hard line across the calendar. On that day, 32E Atlas slips into the blinding region behind the sun, cutting off every single Earth-based telescope. The geometry is relentless. Earth, the sun, and the object will be locked in a straight line, with our planet stuck on the wrong side of that blinding light. For nearly 6 long weeks, the most massive interstellar object ever detected will move completely unseen. Its path, its behavior, and any potential changes will be hidden from our direct view. This blackout isn't just a scheduling inconvenience for astronomers, it's a critical loss of data. It means the defining moments of its journey, its perihelion, which is its closest approach to the sun, and any possible orbital maneuver will all unfold beyond our ability to watch. Think about the distances involved. The distance from Earth to the sun is about 150 million kilometers. At its closest point during this conjunction, Atlas will pass just beyond that, at about 1.36 astronomical units away. From our vantage point, no ground-based observatory on the planet, no matter how powerful, can separate its faint glow from the sheer brilliance of our solar furnace. This period of invisibility is where the two stories collide. The mainstream view expects Atlas to loop around the sun and reappear on the other side, its path predictable, its journey unchanged, continuing its exit from our solar system. It will have been baked by the sun's heat, maybe losing some mass, but ultimately following the laws of gravity as we know them for a simple comet. When it comes back into view, it should be right where our calculations say it will be. But Avi Loeb's theory paints a much more dramatic picture. He suggests that during this blackout, Atlas might perform a powered maneuver. By firing an engine or using some advanced form of propulsion near perihelion, it could shed just enough velocity to be captured by the sun's gravity. It would transition from a hyperbolic escape trajectory to a closed, elliptical orbit. Instead of a visitor, it would become a new, albeit very distant, member of our solar system. This isn't science fiction. It's a concept known as an orbital insertion burn, something our own space probes do all the time. The implications of this are staggering. If Atlas is an artificial object, a probe from another civilization, this would be the perfect moment to execute its primary mission without us watching. The sun's gravity provides a powerful assist, meaning the object would need far less energy to change its orbit than it would anywhere else. It's the most efficient time and place to make a move. The question then becomes, why? Why would an advanced intelligence send a probe to our solar system only to have it settle into a distant, lonely orbit? When Atlas finally emerges from behind the sun in mid-December, we'll have our answer. Our telescopes will scramble to find it. If they find it exactly where the standard comet model predicts, then the mystery, for the most part, is solved. It was just an unusually large and weird comet. But what if it's not there? What if it's slightly off course? Or what if it's in a completely different orbit, one that keeps it here with us? If that happens, everything we think we know about our place in the universe could change overnight. We'll be faced with undeniable evidence that we are not alone. So mark your calendars. The end of this year could bring the biggest astronomical discovery in human history. Thanks for watching, and be sure to subscribe for updates on this incredible story. Even the most powerful eyes in the sky, like the Hubble and James Webb Space Telescopes, are sometimes forced to wait. For the interstellar object known as 3I Atlas, this created a frustrating data gap, stretching from late October all the way through early December. Astrometric tracking, spectral analysis, even basic brightness measurements, everything stopped. The only faint hope for a glimpse came from a handful of solar probes and coronagraphs. These are instruments designed to study the sun's violent storms, not faint, distant comets. Their sensitivity and imaging cadence could barely register an object as dim as Atlas. So for most astronomers, the window slammed shut right as the story's most critical chapter was about to begin. Every burning question, is it a natural escapee from another star system or an engineered artifact? Is it a comet or something else entirely? The clock was ticking, and the moment of truth was set to unfold where no one could watch. For astrophysicist Avi Loeb, his attention snapped into focus the moment the early photometry data came in. The initial size estimate for 3I Atlas landed like a thunderclap, 20 kilometers across. To put that in perspective, the first interstellar visitor, Oumuamua, measured less than a quarter of a kilometer. The second one, 2I Borisov, was maybe a single kilometer wide. Atlas, by comparison, was an order of magnitude larger than anything our surveys expected to find first. This number wasn't just a wild guess. It was calculated from the object's brightness, corrected for its distance and angle to the sun, and then modeled against the known reflectivity of comets. With a brightness well above magnitude 12 and no sign of a dense, optically thick coma to artificially boost the reading, the conclusion was inescapable. The nucleus had to be massive. Loeb's skepticism, however, grew from the math. Survey statistics predict that for every large interstellar visitor we find, we should have already spotted thousands of smaller, fainter ones. They're specifically tuned to catch these fast-moving, inbound objects. If this 20-kilometer size estimate holds, it means one of two things. Either our powerful surveys have somehow missed a vast population of smaller bodies, or something incredibly rare and unexplained is at play. This is where Loeb's argument really begins. Finding a 20-kilometer interstellar object this soon defies the power law expectations that underpin all of modern survey science. The statistical alarm bells weren't just ringing because Atlas was bright. They were ringing because its sheer scale contradicted everything we thought we knew about what should be out there. For Loeb, that single number, 20 kilometers, became the first and most glaring anomaly in a growing list. A mass of at least 33 billion tons now anchors 3I Atlas in the record books. This incredible figure, drawn from dynamic modeling and the comet's persistent brightness, dwarfs every confirmed interstellar visitor that came before it. Yet, this is where the paradox truly begins. Despite a vigorous outgassing rate of nearly 100 to 150 kilograms per second, dominated by carbon dioxide, there is no measurable non-gravitational acceleration. In comet science, this is the classic rocket problem. When a comet heats up, the gas and dust that vent from its surface act like tiny thrusters, pushing the nucleus ever so slightly off its predicted path. For typical comets, even modest activity leaves a clear fingerprint in the astrometric record, a slow drift, a subtle curve away from a path dictated by pure gravity. But the Minor Planet Center's global dataset, which includes over 4,000 positional measurements of Atlas, finds no such deviation. The upper limit on its non-gravitational acceleration is less than 1.5 meters per day squared. That is so astonishingly low that for its observed activity, only a truly massive object could remain so unmoved. The numbers only sharpen the contradiction. If you take the measured gas production, multiply it by the outflow velocity, and then divide it by the estimated mass, the expected acceleration should be clearly visible in the data. The only way it wouldn't be is if the nucleus is not just large but remarkably dense. Or if the outgassing is perfectly balanced in all directions, an unlikely scenario. Monte Carlo simulations have been run, sweeping through every plausible combination of nucleus size and density. For anything smaller than about 5 kilometers across or less dense than solid water ice, the math completely breaks down. The outgassing would have kicked Atlas off its predicted track long ago. Only a massive solid body fits both the photometric and the dynamical evidence. Alternative explanations, like jets firing in perfect opposition to each other, or the object being a swarm of loosely bound fragments, require finely tuned physics and improbable geometry. The mainstream model struggles to reconcile the numbers without invoking statistical flukes or special pleading. For Loeb and his colleagues, this isn't just a curiosity. It's an open invitation to think outside the box. If the mass is real and the acceleration is absent, the door to non-natural scenarios remains ajar. Survey science is built on numbers, lots and lots of them. For every giant object like 3I Atlas, population models predict the sky should be filled with thousands of smaller, fainter interstellar wanderers. The logic is simple. Smaller bodies are far more common in every known asteroid and comet belt. If our discovery pipeline is working as it should, the very first interstellar objects we find should be the tiniest ones, the ones that outnumber the giants by orders of magnitude. But the record tells a different story. The Pan-STARRS survey, the Atlas network, and now the Vera Rubin Observatory have scanned the sky for years, logging millions of detections. Their sensitivity has improved to the point where they can spot incredibly small objects. Yet, the data continues to present us with these perplexing anomalies. Have you ever looked up at the night sky and wondered what's really out there, hurtling through the dark between stars? For a long time, we thought we had a pretty good idea. We expect to see small, faint objects first, a slow trickle of discoveries at the very edge of our detection capabilities. The first 2 interstellar visitors we ever found, Oumuamua and Borisov, fit this pattern perfectly. They were tiny, dim, and just barely visible. Then everything changed. Without any warning, a behemoth appeared, 3I Atlas. This thing was a monster, 20 kilometers wide, weighing at least 33 billion tons, and blazing so brightly it shattered all our expectations. It wasn't a faint flicker. It was a cosmic searchlight. This created a huge statistical puzzle. If an object this massive is typical, our surveys should have already spotted hundreds, maybe even thousands, of its smaller cousins. But they haven't. The grand total of interstellar visitors is just 3. Astronomers at major observatories started raising red flags. The odds of finding a giant like Atlas before finding its much more common, smaller relatives are astronomically low. Some calculations put it at less than 1 in 10,000. It's like finding a blue whale before you've ever seen a minnow. The fundamental rule of cosmic populations, the power law, seems to be broken. Either the universe is hiding a colossal, unseen population of faint objects, or 3I Atlas is an outlier so extreme it defies all known science. For anomaly hunters, this isn't just a curiosity. It's a signal that our understanding of the cosmos is fundamentally wrong, and the story of Atlas is just beginning. As if its size wasn't strange enough, the path of 3I Atlas through our solar system is even more bewildering. It's hugging the ecliptic plane, the flat disk where all our planets orbit, with a tilt of only about 5 degrees. Think about that. An object from the chaos of deep space should slice through our system at a steep, random angle. Instead, Atlas is gliding almost parallel to our planets, like it belongs here. It's taking a route normally reserved for homegrown asteroids and comets, and the plot thickens. As it approached the Sun, Atlas executed a series of breathtakingly close flybys with major planets. First, it zipped past Mars, missing it by what is, in cosmic terms, a hair's breadth. Then, its trajectory lined it up for close encounters with both Venus and Jupiter. This is a sequence of planetary flybys so precise, it looks more like a carefully planned NASA mission than a random celestial event. The probability of a massive, high-speed object threading such a perfect needle through our solar system is almost 0. We're talking odds of less than 1 in 1,000. This isn't just a cosmic coincidence. This highly specific path put Atlas in the perfect position for gravitational tweaks from each planet, fine-tuning its journey toward the Sun. It's almost as if the trajectory was designed to set up a dramatic maneuver at its closest approach to our star. The flight path itself has become a silent clue, raising profound questions about whether this was a natural occurrence or something else entirely. When we finally got our first good look at Atlas, the images were deeply unsettling. Instead of a classic comet tail streaming behind it, there was a concentrated, powerful glow on its front, facing the sun. This forward brightness was so intense that imaging teams at the world's best telescopes scrambled to find a technical glitch, but the anomaly persisted. Then, as it got closer to the sun, the forward glow faded and a normal tail appeared, as if a switch had been flipped. Was this a crust breaking apart, or something active happening under its surface? The mystery deepened when the James Webb Space Telescope analyzed its chemical makeup. It found that Atlas was spewing out carbon dioxide at a rate nearly 8 times that of water. For comets born in our solar system, water is almost always the dominant gas. This bizarre ratio suggested Atlas was either perfectly preserved in a deep freeze far from any star, or was covered in a strange layer of carbon dioxide frost. And then another surprise. Weeks before it was expected, a sudden brilliant green glow erupted in the cloud of gas surrounding Atlas. This green light, caused by carbon molecules fluorescing in the sun's radiation, normally appears when a comet is at its hottest. But Atlas lit up early and bright, defying all our predictive models. From its impossible size and improbable orbit to its baffling chemical behavior, 3I Atlas is not just another rock from space. It's a profound anomaly that challenges everything we thought we knew. The data is in, but the real story is just getting started. The strange color change we saw raised a whole new set of questions. What's going on with the layers of ice on this comet? What is its surface chemistry really like? Every new anomaly, whether it was optical, chemical, or chromatic, just piled more uncertainty on top of everything else. And with the comet about to slip behind the sun, any answers would have to wait. Its true nature is left hanging in the balance, somewhere between a scientific artifact and a mind-blowing revelation. Avi Loeb's entire case hinges on a window of time so brief it barely registers on the cosmic clock. It's like an interstellar bullet, arcing just 1.36 astronomical units from the sun. For any object on a path like this, a hyperbolic one, this is the one moment, the single instant, where a change in speed of just a few kilometers per second, could tip the balance from escaping our solar system, forever to being captured into orbit. The physics here are absolutely unforgiving. To swing from an outbound interstellar trajectory into a bound solar orbit, Atlas would need a change in velocity, or delta V, of roughly 8 kilometers per second, delivered at that exact moment of closest approach. Anything less and the comet just races on, never to return. And here's the kicker. This maneuver, if it happens, will be completely invisible to us. The sun's glare will blind every telescope on Earth. Even our best space-based instruments, designed to block out the sun's light, will struggle to pick out a faint, fast-moving speck against that bright solar background. The detection limits for these instruments are far too bright for a comet like Atlas during this solar conjunction. The practical effect of all this is that any change in its trajectory, any burst of activity, or any kind of engineered thrust would slip past us completely unnoticed until the comet re-emerges weeks later. There was a brief glimmer of hope with the Mars flyby on October 3rd. It passed just 29 million kilometers from the red planet, and scientists debated whether the high RISC camera on the Mars Reconnaissance Orbiter could get a direct image. They ran the numbers, but it was a no-go. At that distance, a 20-kilometer object is smaller than the camera's own resolution limit. Even as a point of light, Atlas would be too faint. For Loeb and his supporters, this forced invisibility is both a source of frustration and a massive opportunity. Trajectory quirks and planetary flybys? Just coincidence, multiplied by the vastness of space. Other prominent astronomers echo this stance. They point to things like selection bias in our surveys and the simple fact that comets are notoriously unpredictable. For them, the burden of proof lies squarely on those making the extraordinary claim. Loeb, however, approaches the exact same data from the opposite direction. He doesn't use a formal scale, but his argument is about stacking the anomalies, its mass, its size, its alignment with our solar system's plane, its planetary encounters, its chemistry. He argues that the more these strange features cluster together, the stronger the case becomes for paying very close attention. In his view, when enough oddities pile up, the only responsible move is to maximize our observations, especially when a rare event like passing behind the sun could conceal a defining maneuver. The principle is simple. If the list of outliers gets long enough, you have to treat the object as if the stakes are incredibly high. The next critical window opens in early December, when Atlas re-emerges from its solar conjunction. Every major observatory will be primed and ready, looking for changes in its orbit, rotation, and spectrum. If it doesn't, the debate will enter a whole new electrifying phase.